Thank you for the introduction, Miroslav. Yes, my name is Mosin. I'm industrial PhD at Volvo Cars, and I'm working together with my two supervisors, Miroslav and Darko Durisic from Volvo Cars, on the develop project. And then this particular presentation is about our small study on comparing input prioritization techniques for testing deep learning algorithms. So probably in the beginning, a few words about our develop project. It's an acronym from the architectural design and verification validation of systems with machine learning components. So basically, we are looking into different research directions related to the architectural design and testing of machine learning systems. Because traditional systems, they are different from machine learning systems, and machine learning brings stochasticity into the system, and we need to account for these changes, and therefore we need to design new architectural patterns, and also we need to think about new ways of verification and validation of such systems. And I will not talk about the architectural part today, but I will present our small study on the testing part, in particular on the test input prioritization. So what is this task? It's an important task in testing of any system, and in particular in testing on deep learning algorithms and models. So the goal of the prioritization is to sort the test inputs in the test set such that prioritizing the highest probability of making an incorrect prediction for the test input. So we want to test the more prone for errors test inputs in the beginning of testing. As you can see on the picture, for example, if we look here, we have different prioritization orders, 3 different prioritization orders, and we can see how cumulative number of errors grows during the testing, and the orange one will be ideal prioritization for us because we reveal all of the errors in the beginning of testing, and then we just test the inputs which do not reveal any errors for us. The blue one will be poor prioritization technique because it's kind of random sorting of the test inputs, and the revealing of errors will be slow in this case. And of course, we want to have as much as close to this orange line. And in this case, we can reduce, first of all, the testing time, because we can just put a threshold here and revealing all the errors in the beginning, and we don't need to test the rest of the test inputs. And also we can save cost on the labeling of the test inputs, because labeling of the test inputs in deep learning especially is very expensive, and if we prioritize test inputs in a smart way, we don't need to label the rest of the test set, like in the case of ideal prioritization. So this is the task, and an important thing also is that, for example, in this testing machine learning based system systematic mapping, the authors distinguish between 3 different types of deep learning testing techniques. We can say that this is applicable for all of the testing techniques, but also for test input prioritization in particular. And these 3 are white box, data box, and black box. So what is a white box testing techniques? These are techniques which work based on the information from the algorithm itself, like, for example, the architecture of the neural network, or, for example, neuron activation statistics of the neural network. So we do need to have this access to the neural network to apply these white box testing techniques. That's why they called white box. Black box, it's also similar to the traditional testing. The idea is that we don't need to have an access to the algorithm itself. We just we can just apply the testing technique without having an access to the system under test. And for deep learning, we can also set aside so-called data box techniques, why they call data box, because they don't need to have an access to the algorithm or system under test, but they do need to have an access to the data, for example, training set. And we cannot say that this is a black box completely, because we need to have an access to the data. So we have these 3 different access levels for different testing techniques. And in this study, we were going to compare these 3 different types of techniques between each other, because in the literature, we didn't see anything similar to what we did in terms of comparing different types of testing techniques according to the access level to the system. And we think that this is very important from the industrial point of view, because the access levels play a key role when we develop algorithm and when we work, for example, when we talk about the relationship between the OEM and suppliers. For example, supplier providing an algorithm as a black box to the OEM, and then OEM can only apply the black box testing techniques. Or in other situation, they can apply white box, for example. So there are pros and cons of these methods, and in this particular research study, we were going to answer these 2 research questions. So we want to compare these 3 different types of techniques in terms of their effectiveness when testing deep learning algorithms. Effectiveness, we mean here that how well the input prioritization technique can prioritize the test set. And also we want to compare them in terms of efficiency. And by efficiency, we mean here the time for setup and the execution of the techniques. So next, I will explain briefly these 3. So we selected 3 different techniques from 3 different groups of 3 different types, which I explained before. So the first one is a white box technique called surprise adequacy approach. It's a popular testing technique, and it can also be applied for input prioritization. And it's based on so-called activation traces, which are just the neuron activation statistics. So the idea is to estimate how surprising or how unusual is particular activation trace for the particular test input is, and based on this surprise score, we can sort the whole test set, and then according to this sorting, we start the testing. So we firstly test the most surprising test inputs, and the assumption is that the most surprising test inputs will be probably more error prone for this particular network. So white box, because it uses the neuron activations inside of the system under test, which is particular neural network in this case. And on the right of this slide, you can see the workflow, or the bottom line is a machine learning workflow where we have the setup and training for the algorithm itself, which we want to test. And on the top, we show the testing workflow, where we set up and execute our test input prioritization technique. And so the idea of this picture is to show that we start the testing workflow where we set up and execute this prioritization only after we train the model. So we cannot start it early because we need this trained model to get this activation statistics or activation traces. And only after that we can execute the prioritization. And then we get prioritized test inputs, or images in this case, for example, and then we start testing. So this is the white box technique. As a data box technique in our study, we use an autoencoder-based approach for test input prioritization. So autoencoder is a particular type of a neural network which is used to learn the hidden representation of the images by training the network to reconstruct the input image through the compressed representation in the middle of the network. And how we can use this? So it's a separate network. We don't need to. So this is not a system under test. So this is a separate network, and we train. The assumption is that if we train this network with the trained data, and then we use this autoencoder trained model on the test set, and then we try to reconstruct the test set images. And if we get a good reconstruction, meaning that we have a low reconstruction error, then this particular test input is not unusual or is not surprised. And if we have a high reconstruction error, for example, if we didn't have similar images in the train set, then the autoencoder will most likely fail to reconstruct the image with a good performance, so it will have a high reconstruction error. So we want such images to test in the beginning of testing. So we use the autoencoder to sort the test set according to the reconstruction error in the decreasing order. So we firstly test the images from the test set with the highest reconstruction error and hope that they will reveal, so they will be more error prone for the system order test. And the workflow also on the right side of the slide is to show that since this is a data box technique, we don't need to have an access to the training, to the trained model under test. We can start the setup and execution of the prioritization at the same time when we start the training and when we start the setup and the training of the system under test. And then we have prioritized images, and then we can start testing. So yeah, and this is data box because, yeah, as I said, we don't need to have an access to the model, but we do need to have an access to the training data in this case. And as a last type of the prioritization technique, which is a black box, we use the similarity-based method, which we adapted from the traditional testing. So similar to the traditional testing, the similarity-based approach is based obviously on the similarity of the test inputs. Yeah, for example, on the similarity of the images when we talk about image classification task. And the assumption for this method, why it should work, is that if we so the similar test inputs will behave similarly for the network, meaning that, for example, if we found the one test input which for which the network fails, then probably the similar input will also for the similar input the network also will fail. So this is the idea of similarity-based approach. Yeah, the same workflow here, and we show that the setup time here is negligibly small, and I will explain it later, probably if I have time, why it is. But yeah, the idea is that we also can start the prioritization at the same time when we start the training the model, so we don't need to wait for the trained model. Yeah, this is a brief introduction into the three techniques which we used of different types for the prioritization of the test inputs, and going next to the experimental part. So obviously we couldn't test all of the possible deep learning tasks, but we started from the simplest one, which is image classification task. And in our case, the system order test was just the usual convolutional neural network with convolutional and pooling layers. Yeah, this is just as an example of how it looks like, but we use the particular architecture which we described in the paper. And for the data, we also started with the simple data sets for image classification, 2 grayscale data set, MNIST and fashion mist, and 2 color data set, CFAR10 and STL10. These 3 data set, MNIST, fashion mist, and CFAR10, are small scale data set, which is 32 by 32 pixels. And we, in the end of the study, we also decided to try the high resolution images, 96 by 96 pixels. so the separation into training and test images is already done by the creators of the dataset. So we used the default training testing split to be consistent in our experiments. So the system other test was trained using the training images here, and then we tested this system on the test images. So, but firstly, we prioritized these test images in the beginning before testing using these 3 different techniques, which I explained just before. And so this slide probably is the most important slide describing the results. Probably I spent a few minutes here explaining how we actually measure the efficiency. So how well the technique sort the test inputs. So just take this one, for the NIST dataset, this result, and see how. So what we do here, we just prioritize test inputs using different techniques, and then start testing from the beginning of the test set, and then we measure how the cumulative number of errors grows during the testing. And obviously, the closer the line goes to the ideal prioritization, the better. And as a numerical score, we compute the area under the curve to represent the efficiency of the technique for prioritization of the test inputs. So for the NIST dataset, we can see that. So yeah, I forgot to mention that LSA and DSA, it's 2 different variations of surprise adequacy white box technique. They perform best across all different data set. The red one and the green one is the autoencoder technique. Also, we tried with traditional autoencoder, and also we tried the variational autoencoder for the data box approach. So for the NIST data set, it shows like a medium result, better than a black box similarity-based approach here. But for the rest of the data set, the data box autoencoder techniques and similarity-based approach performs similarly, but worse than the surprise adequacy in all of the cases. Probably also important note is that the variational autoencoder works better than the traditional autoencoder in all of the cases for all of the data sets. Yeah, so probably I will not explain the numbers here, but go next to the efficiency. So we measured the 3 different times. The first one, this is the setup time of the technique, which, yeah, for example, for the autoencoder technique, setup time is to train autoencoder. We think that we consider it as a setup time. For the similarity-based, there is no setup time because we just pick the test input and compute the similarity scores. And computing the similarity scores, we consider as an execution time. So if we look into the first 2 rows for the white box surprise adequacy approach, we see that the general setup time it's very big because we include here also the training of the network, because then we cannot start prioritizing test inputs before we get the trained model. So we include it in the general setup time. But once we have the trained network, then the setup time of the technique itself is small, and the execution is the highest one. So the slowest one across all of the other techniques. The autoencoder have the execution time between the surprise adequacy and black box technique, similarity one, and similarity is the fastest one without any setup time and very, very small execution time. Yeah, and this is just the research questions in the answered form. So about effectiveness, we say that the surprise adequacy approach, which is white box techniques, is the most effective, which we see from our experiments. And here we put the numbers from 0.7 to 0.9, just for comparison. For example, the autoencoder and similarity-based approach, they are less effective with moderate performance. And here are the numbers. Yeah, just for understanding how less effective they are comparing to the surprise adequacy approach. And the efficiency, in terms of efficiency, the similarity-based black box approach is the most efficient without any setup time and the shortest execution time. The autoencoder-based approach somewhere in between, and the surprise adequacy white box approach is the least efficient in our experiments, 2 times slower than the autoencoder, and around 12 to 19 times slower than the execution time, around 12 to 19 times slower than the autoencoder-based approach. We also put the results in this form of the table. The idea was to put it in such a form for practitioners which decide to use our results when they decide which technique to use for the industrial usage. Surprise adequacy, it's a white box technique. We need to have an access to the network, which is probably cons of the disadvantage of this method. And also we need to have an access to the training data. It has the longest general setup time and execution time. But if the network under test is already trained and only test sets are changed, then the setup time is pretty fast. So we don't need to retrain the network under test. Then we just apply this technique on the new test set. Effectiveness, it has a high test input prioritization performance. It's stable across different experiments in our study. So the autoencoder technique is a data box, and which means that we need to have an access to the training data. It has medium or moderate setup and execution time. And if the training data is not changed, but only the testing data is changed, we don't need to retrain the autoencoder. We just apply it on the new test set, which also saves time. And it has moderate test input prioritization performance. And similarity black box technique, it's the advantage of this method that we don't need to have an access to the training data, and also we don't need to have an access to the model itself, to the model under the test. So this is good in case of industrial usage, as I gave an example in the beginning, when the original equipment manufacturer receive the train algorithm from the supplier in a black box format. And in this case, we cannot access the internals of the models to apply white box surprise adequacy approach, for example. Then similarity-based technique can be as an alternative solution. And if you don't have a training data also, but if you have a training data, probably autoencoder can be also used. So the black box technique has the fastest execution time, and no need for setup time, and but the performance is also moderate, so it's worse. It's it's worse than the white box technique. And white box, obviously it's better because we have more information. We have information from the network. So yeah, this is the table which we think can be useful for some of the practitioners, but of course this is, as always, just a beginning of this research direction, and we started with a simple task, which is image classification task, and we started with a simple data sets, or open toy data sets from the internet. But so the next things which we think can be and should be done to explore these input prioritization techniques of different access levels further. So we need to also test more real-world algorithms which used, for example, in the perception in the automotive domain, such as object detection and semantic segmentation tasks. in addition to image classification task. And also we need to consider different model architectures under test, different variations of the techniques themselves, because there are some fine-tuning parameters which can be changed. And also the data sets, we need to increase the complexity of the data sets further in order to get to get better and to be more sure in the results, in the conclusions which we make here. But based on the experience which we done, we make these kind of conclusions which I presented. So yeah, I think that this is it. Thank you for listening.